Good morning, everyone.
Morning.
Ask me any questions while we're waiting for everybody else to log in.
I have a question. For the lab, there was no link to post it last night.
Oh, geez. Yeah.
Yeah, I was going to ask that
I think
too.
I just read your email about that as well. Yeah, let me do that real quick while you're here. Can't believe I screwed that up. All right, let's see. I must have turned on the wrong one because I remember doing it, but right.
I joined late. Excuse me. I joined late. Are you talking about the submission link for the lab for today?
Yeah, the propagation lab.
Yeah, I thought I made that already too. I'm looking at the lab right now. Let me double check. I'm just not. Huh. Yep. I did this. I don't know why. Let's see. Edit. Oh. Huh. That's weird. I guess I don't know what course I did it in. Maybe I just did it on the on 241 classes instead of 242. I'm fixing the submission button now. Anything else while we wait?
Also, I wasn't able to find the practice respondus. I don't know if that was something that was supposed to be.
I'm working that out. I'm probably going to do it immediately after class or like during your lab or something like that. So I've almost got it finished. It should be available really soon. And the test is going to be a week from today. I think it's the 14th. And remember, I'm actually giving you 2 hours to do that. So our class meets at 11. What that means is I'll let you start as early as 10:15, or you can start as late as 11 and finish at 1:15, or 11, finish at 1. So that if you can't fit that in your schedule, make sure you let me know so I can adjust that. In other words, what I have to do is I'll make a different test for those people that can't fill it in at that exact time. I have to make a different test for you guys, and y'all can still probably take it through Respondus and all that. You just have to take a different one because otherwise someone could take it, tell you what's on it, and then all that crazy stuff that no one probably does, but just because there's a chance, I have to do something about it.
So you're talking about the midterm, right?
Yeah, that's the midterm.
Okay, just making sure.
Yeah. I now have the October 4th to October 10th week open. I had published everything, but I hadn't published the actual module for that. So that was the problem on that one. And it looks like everything's there. Yes, good. Okay. So thanks for catching me on that one. It's always helpful to get this stuff done properly. I've got that done now, and one last thing before okay, now I should be good to go. Let me get all this junk out of the way. So we're still in chapter 27. You'll notice the midterm only goes through chapter 26. I'm going to stick with that, so that'll be fine with me or whatever. That just means you've got plenty of time to practice 21 through 26, and the actual lab should be, or the actual practice test, the version that's not Respondus, should all already be up. I will double check on that now that we're here. D01B modules, that one I know is fixed, and let me see if it is. No, it does not appear to be. Hold on, maybe I'm looking at the wrong thing. Okay, I see what's going on. There was one that was made, but it's for chapters 21 through 30. So no, I will do all those. Those will be those practice tests. Both of those will be done this afternoon sometime, probably while you are doing your lab. So any other questions? I just let 3 more people in. I think that's about the right number. All right, when we last spoke, I had introduced you to the concept of force acting on a current carrying wire using the famous F equals Bill equation, which we actually write as F equals I dl cross B in terms of vector. In other words, if the force varies or the current varies, over the path or over the length of the cord that's carrying the current, then you have to actually integrate little segments. And we did a problem sort of like the one in the textbook. In fact, it turned out to be the same one as the textbook, but in fact, the current just went the opposite direction as the one in the textbook. So that's sort of a tough problem, but you'll see it as long as all of the current carrying wires are coming radially towards the center of a circle, or they're actually on arcs of the circle, then you can compute that all day long. And it's actually a very straightforward little process. Like I showed you then, I showed you all the gory details, but there's a easier way now that you've seen what the gory details are. You can sort of hopefully better follow what the author did on his version of the example. So check that out. That should be good to go. Now all we got to do is I need to talk to you about magnetic dipoles. So we've already did the Lorentz force law. I've shown you how to calculate, for instance, the frequency for basically a type of accelerator thing, where basically when you send an electron or a proton into a magnetic field, if the velocity is exactly perpendicular to the magnetic field, then it'll just spiral around and around. Right? They call it the cyclotron frequency, and the frequency of that is the cyclotron frequency. However, if you have a component that is actually parallel to the magnetic field, so I was saying like that this is a positive particle moving this way. So using my right hand, that particle is moving this way. If in fact the magnetic field points up as the as the positive particle is going this way, then the force will tend to make it spiral. And of course, the spiral is in the direction of my thumb. So it's actually going to cause it to do this in this way. But if we have a component parallel, that motion is going to continue and have no acceleration whatsoever. So instead of a nice flat spiral, if it had a component this way, then it would actually spiral up like this in the helix. And that's not unlike a conceptual example your book talked about. You just remember the velocity would be the same. The component that's actually parallel to the magnetic field, that velocity is not going to change at all. So all you really need to do, like if you want to calculate how long it'll take to get 12 meters high, you just divide the 12 meters by that component of velocity that is parallel to the magnetic field, because it's going to go unabated vertically if the magnetic field was pointing up and the positive particle is going to the right. Okay. So now what I want to do is, since we did that and I showed you Lorentz force law, I want to let you think about it's actually a very common device. You might not realize it's that common, but it is a very common device. But basically, I'm going to imagine a little loop of wire. So there's a little wire. It'll come up and make a rectangular loop. I could make it any shape I wanted, but rectangular is easier to do the derivation. And then the result we get will be absolutely correct for all scenarios. So let me show you what I mean by that. Turn on my document cam. So what we have is you need to have some kind of axle, if you will. And this should actually be back behind where you can't really see it. This one you can actually see. And that could be like the axle. And so you can imagine it's got bearings or something to allow this to spin freely. Get a better focus. And then what you'll do is you'll have a wire that runs right along here, comes out, goes up here, attaches there, and you could actually imagine the wire as if it has some thickness. And let's say it's free to spin, and we're going to have a current I going in here and a current I coming out here. Okay. So this thing's going to spin like this. And what I'm going to do is imagine a magnetic field, let's say pointing upward. So let's say we have a magnetic field pointing this way. and it's essentially uniform. And this might seem like a really contrived situation, but it's exactly the situation that you'll find in your alternator, in your washing machine, in your dryer, just about everywhere there's an electric motor, some device like this exists. And normally what they do is they can make it even more powerful by not going in one loop, but going around a bunch of loops and then coming out. Okay. Well, I'm going to say this dimension right here is Y, and I'm going to say this dimension right here is X, and I'm actually assuming the wire is infinitesimally thin, so I'm really not concerned whether it's the inside edge, the middle, or the outside edge. So I'm just taking roughly that. So when you do this, you see if this current's going this way, that means we're pretending like positive charges are going this way, this way, this way. Again, these are positive charges. And then of course, they're also going this way, or excuse me, drew the wrong way, that one, going this way like that, okay? So if you look at this side, right here, you've got positive charge Q going in the same, going in the direction V. Since it's positive, the QV is the same direction as V. You use your right hand, you need to curl your fingers towards the magnetic field. So I have to lock my hand down from any of these positions to this one right here, because that's the only way I can curl my fingers towards the direction of B. Or I can use the other alternative method, which is the current is my index finger, the current, or the QV is my index finger, the magnetic field is my middle finger, and then my thumb points in the direction of the force, which is out of the page. So you can see right here, we've got a force pointing out of the page, which I'm going to say is in the red direction. Okay. And then for this part over here, obviously that's just the opposite. So that part's going to be into the page, and this part's also going to be into the page. And in fact, this little part right here is really supposed to be minuscule compared to this group. So really this amount of force here and here are going to sort of cancel each other out. They'll try to sort of flip the thing this way, but it's not going to allow it to happen. Now, when you get over here, you can see, for instance, here, QV is that way. And the magnetic field, of course, is upward. So with the magnetic field upward, you can see that the B and the V are actually parallel. So no force comes from that. And then with this one, you say this, well, that's anti-parallel, so no force comes from that. So if you set up this situation with the magnetic field this way, then you're not going to get anything to rotate. So to get it to rotate, we need to try a different scenario. So I'm going to draw it a little less precisely this time, just because of trying to get through quickly. I'll make the spindle a little more precisely though. So I'll do like this, and I'll do like this. And again, we're going to assume it's a distance X from here to here, and a distance Y from here to here. Again, we have another spindle over here that's supposed to be exactly lined up. And again, it can rotate freely this way. But now we're going to put the magnetic field in a different orientation. We're going to make the magnetic field, say, go to the right. So I'll use a green marker this time. So now we're in a uniform magnetic field going this way. Okay. So we've got a current coming in this way, I, and coming out this way, I again. I will draw the current direction in red. So right now, there's a current going that way, there's a current going that way, there's a current going that way, and there's a current going this way, and then of course this way and this way. So if we now look at each of these parts and see what's happening, we can see if this is actually going to give a tendency to rotate. This one gave a tendency to rotate, but only this way, which we didn't allow it. So if I actually make it parallel to, say, the long side in this case, what you see is, remember, conventional current is positive charges moving in the direction of the conventional current. So this one right here is obviously a QV that way, and then you got a B that way. So the magnetic field is causing a force downward on this part, or into the page, I should say. So into the page is F there, and then out of the page is the F there. Okay. Over here, you see it's actually parallel or anti-parallel to the magnetic field. So the F is 0. And same thing here, the F is 0. And then over here, it's actually parallel as opposed to anti-parallels, but still you get F equals 0 here and here. Now over here, you get QV that way, the magnetic field that way, and my thumb now with my right hand is pointing downward. So in this case, I get a force going downward, which is exactly what we expected because that's what we got down here as well. Now over here, it's exactly the opposite. So I'm basically should know from that I'm going to get a force pointing outward this way. Okay. So really the only forces that matter, these don't have a very big lever arm to rotate this. So I'm trying to calculate the torque. And remember, torque is equal to R cross F. That's normally the way you do it, where R is basically the distance from the application of the force to the center of the rotation. Okay. So I can see from this side right here, I'm going to have a force equal to, at least in magnitude, it'll be equal to I times B times, we called that Y. Okay. This one will be the same force now, I times B times Y. Now the torque on this side would obviously be X over 2. And of course, the torque on, the lever arm would be X over 2. Similarly, the lever arm over here would be X over 2. So what we're going to get is torque is going to be X over 2 times I B Y plus X over 2 times I B Y, which when you add them, you get I B X Y. Well, X times Y is just the area of this. And it turns out, even though I'm doing this for a rectangle, this is also true for a shape that would be a circle, which is what they're normally made of. So basically we get B times I times A. And remember, I told you, you can even do more by wrapping more turns around that. So what we're going to do is we're going to say this quantity right here is our dipole moment, or our magnetic dipole. Okay. And in fact, we're going to generalize it to allow n number of turns. So what we're going to do is we're going to define a dipole vector. And that's equal to n times I times A. So n is the number of turns, I is the current going around it, and A is the cross-sectional area. And then we're basically going to say that points in the direction of the A vector, and the A vector is defined in terms of a right-hand rule. So yeah, another right-hand rule. What you do is you take your right hand and you curl your fingers in the direction the current is going. So the current's going around this way. So that means that. So in this case, the A vector would actually point into the page. So by doing that, we can see that now I can treat this as a mu vector, and then I got to just cross it with instead of the actual force, because this is I'm just a little bit shy of the force. In fact, all I need to make the force is now to add a B. So in fact, torque is going to be equal to mu cross B. And that's the equation we were shooting for. And that's called the magnetic dipole. And if you remember in chapter, I want to say it was 21, but it might have been 22. I'm going to pull that up real quick. If we look at chapter 20, towards the end of 21 or the beginning of 22. Yes. And electricity, we found that torque was equal to P cross E, where P was the electric dipole moment, or specifically P was equal to Q times D. Okay, so that's the electric dipole moment. And you can see that now the magnetic dipole moment looks exactly the same. Well, we also found when we tried to do the actual work done and say rotating this object, we found that work is equal to the integral of tau d theta. And again, I'm going back to the electric case for a brief second, just to remind you. And what we did for that is we have to take the torque, which you can see from this becomes P times E. So we just get work is equal to P times E. And in this case, we're actually going to make it a negative because the P and the E are actually not in the same direction. So we'll say it's equal to negative P E integral sine theta. Okay, because remember, P cross E is really magnitude of P times the magnitude of E times the sine of the angle between them. This is really not very well focused. That looks a little better. Okay, when I integrate that to some arbitrary amount, I basically get positive P E cosine theta, which lo and behold looks a lot like, and of course that's the range of integration from say theta 1 to theta 2. So I end up getting something along the lines of P E times cosine theta 2 minus cosine theta 1. And since the potential energy U is equal to the negative change in work, negative change in work, that's the very definition of potential energy. Ooh. I don't know why I said that. The change in potential energy U is equal to the negative of the work done. So now I can say, oh, well, this must be negative P dot E. Okay, so that was the result that we had again for electricity and the electric dipole. So the potential energy is negative P dot E. Now, when we do the exact same thing for the magnetic dipole, we say, okay, well, work again, which is the negative change in U, okay, is equal to the integral of tau d theta. Well, we just found that tau, the torque, was NIAB. So we'll say this is going to be NIAB. Okay, and then of course it really was a cross product, so I have to put a sine theta in there as well, and then a d theta. Oh, I left the d theta off this. Okay, so the integral of sine theta, of course, becomes cosine theta, or negative cosine theta, I should say. So I get negative NIAB cosine theta again. In this case, you can see that plus a constant, say, but we only care about change in potential energy. So what we'd say is the potential energy, or the change in potential energy, is actually equal to negative mu, because there it is, NIA, dotted with B. So there's another equation that we're allowed to use. And the reason why I'm pointing out the electric dipole stuff is to let you see that, in fact, electricity and magnetism turn out to be just two sides of the same coin. And this is further showing that there exists a thing called a electric dipole that if you cross it with the electric field, you get a torque. Well, guess what? There's a magnetic dipole that if you cross with the magnetic field, you'll get a torque. And there's a electric dipole that if you take the negative dot product of it with the electric field, then you'll get the potential energy. Similarly, there is a magnetic dipole that if you take the negative of the dot product of it with B, you get the potential energy. So all of this is just pointing to something really big, and it's the overall thing that electricity and magnetism aren't different forces. They're in fact the same. And one of the problems you do in a typical undergraduate, but maybe junior, senior level class is you can say, imagine this wire right here. So here's a wire. It's got a bunch of positive charges moving this way. Okay, so that means the current's going that way. So that actually establishes a magnetic field. Remember, I said if you put your thumb along the wire in the direction of the current and curl your fingers around it, that means that establishes a magnetic field coming out of the board on this side, or coming out of the page on this side, and going into the page on this side. And out here in front, it'll go to the right, and back there behind, it'll go to the left. So it's a circle basically, and that's the magnetic field. Well, if you jump to a reference frame where these particles aren't moving, in other words, you jump to the frame at their drift velocity, then there's no way you can actually have a magnetic field because there's no current. Well, it turns out if you use special relativity, you can actually figure out that now that you've jumped to that frame, basically length is contracted to such an extent that now the spacing of the positive particles versus the negative particles is different, and creates in fact a uneven amount of electric field that is exactly the same in magnitude as the magnetic field, but pointing the same direction as well. So that's what I'm meaning by this deeper understanding that magnetism and electricity are very much two sides of the same coin. Okay, again, that concept might be a little big for you to grasp right now, or at least for you to completely understand, but just know that is it. What one person might find as a magnetic field, another person might find is exactly physically equivalent to electric field. Okay, so we now have those two results, and we could actually, do neat things like calculate the magnetic dipole moment of, say, an atom, or find the torque on a coil or something like that. So let's do one of those rather simple examples. Let's do let's say we have a coil that has a let's say a 6.00 centimeter radius, carrying a current of, whoa, I don't know why I just dotted my O, but I did. A current of, let's say 1.00 amps, and has 1,000 coils. I'll say equals in, then I can just leave it there. If it is in a 2.00 Tesla magnetic field, that's a strong magnetic field now, what is the max torque and B, the max potential energy. Okay, so we're trying to figure out those two quantities. And by doing that, I really want to know not only how big they are, I want to know in what orientation does it have to be. So let's say we're looking at a magnetic field that goes from left to right. So let's say B points this way. Okay, first I'm going to calculate part A, which is the torque. And of course, torque is equal to mu cross E, or excuse me, cross B, sorry. And of course, B is to the right. So B could equal B0, let's say I hat. If I make my coordinate system look like this. So I got a y-axis here, x-axis here. Now, if that's that, then I want mu to be perpendicular to that, because remember the magnitude of a cross product A cross B has a magnitude equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And of course, sine looks like this. So you see sine's a maximum when the angle is 90 degrees. So we have a maximum when mu, which is, remember, mu is equal to NIA vector. So when A vector is perpendicular to B vector, that's when it's going to be a maximum, and it'll just be B times A. So if the magnetic field's this way, then we can either point the A vector, which is the mu vector, into the page or out of the page, or we can point it left, or excuse me, in the Y direction or in the X direction, because all four of those directions are perpendicular. Okay. So now we'll calculate tau max. So the max is just going to be pi times 0.0600 meters squared times 1,000. So that's N times A. Now I need the I, which is 1.00 amps. And then I'm going to multiply all that times B, which is 2.00 Tesla. So that should give me my whole answer. If I do that math, I'm going to get 3.14159 times 0.06 squared times 1,000 times 1 times 2, and that gives me 22.62 Newton meters of torque. Okay, so that's a pretty significant torque. That's a real quantity, and it happens with, like I said, the ring either oriented this way in the magnetic field. So I'm making the ring. So the ring's either oriented this way or this way. Either of those would cause the same torque. And actually, each way, of course, includes two, but you might actually find that one sort of in some sense, the minimum, because it's the largest value, but it's in the opposite direction. So that's the one case. Now we do part B, and part B is a lot easier because part B is a cross product, is a dot product instead. And what we just calculated was the magnitude of a cross product. So U is equal to negative mu dot B, which equals negative mu times B times the cosine of the angle between them. But remember, cosine looks like this. So cosine's the largest when in fact the theta is 0. So we'll say U max is equal to just mu times B. So in fact, this is mu, this pi r squared n times I times, yeah, because all that's in IA, again, times the magnetic field. So we actually get the exact same magnitude of 22.62 joules. Notice in this case, we call it a Newton meter. In this case, we call it a joule because we're talking about energy. And of course, it can be the negative of that if the A is anti-parallel to the magnetic field. So if the magnetic field is pointing to the right, say, and the area vector is pointing to the left, according to the right-hand rule, then we get the negative lowest potential energy. And then when they're parallel, we'll get the, actually in that case, we get the, that would give us the negative is when they're parallel. We get the positive when they're anti-parallel. So in this case, you can now see when the ring is like this, so A and B are parallel, you can actually get the maximum potential energy. Does that make sense? Anybody have any questions on that? All right, so some time ago, I warned you about the issues revolving around conventional current versus real current. So conventional current is the idea that positive charges are going around a circuit, and that direction that the positive charges go is in fact the direction of current flow. That's what conventional current means. So what we're going to do now is I'm going to show you the instance where that is in fact able to be determined whether it's right or wrong. So here goes. So let's imagine a wire with two different scenarios. So here's a wire. And we're going to say in both scenarios, the current, the conventional current is this way. Well, there's some ways that can happen. Either the positive particles are moving that direction. So we see a positive particle moving this direction, and that's what's actually causing the currents. Or we can do again, this time we'll say, here's the wire, here's the current, but it's actually negative particles going this way. So there's the two scenarios. Well, what we can do is we can subject ourselves to a magnetic field pointing out of the page, say. So let's say this wire is in a uniform magnetic field pointing out of the page. So I'll say maybe here's another one, 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 here's another one. And of course, the same thing is happening to this guy over here. So we got out of the page, out of the page, out of the page, out of the page, out of the page. So what's actually going to happen? Well, if you follow QV cross B, right? QV points in that way, B points this way. So you'd end up getting a force going downward. And in fact, what would happen is we'd end up getting a bunch of positive charges down along this part. Okay. If, however, it's negative charges moving this way, then of course, QV, since Q is negative, is that way as well. Only B is this way. And in this case, we get negative charges going upwards. So in this case, we get negatives, 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 negatives going upwards. Because again, QV, V is this way, but QV, since Q is negative, is this way. And then pointing towards that, actually, excuse me, we get positives. Well, actually, we do get positives up there. Remember, I was saying this, and this is the actual direction it should go. So the negatives will come out down here. Sorry about that. So by default, if the positives go down here, then the negatives will be up here. So in those two cases, you get electric fields, and the electric field points in the direction of that a positive charge would prefer to go under such circumstances. So what I'm going to say is a positive charge wants to go this way in this case, and that's the electric field caused by the charges stacking up. In this case, the electric field points the opposite direction. And you could be able to tell that because remember, positive charges flow in the direction of the electric current, the electric field, but that they also flow in the direction of decreasing voltage. So this would imply, if this is really what's happening, this would imply that this is the low voltage side. But this one would imply that this is the high voltage side. Well, we found out this is what actually happens. Okay, so that's how we can conclude that in fact it is negative charges moving in the opposite direction of conventional current that really carries the charges. So if you want to work out the actual physics of this, now you have to do is say, well, the force is going to be equal to, if you can apply an electric field to cancel this effect out. In other words, yes, these electrons are going to all draw off this way like this. That's what's going to happen to the individual electrons. If you try to cancel that out, then what you'd have to do is apply an electric field in the opposite direction. You say E times E Hall effect is equal to, in fact, it's going to be equal to the force due to the it's going to be equal to the force due to Lorentz force, basically. So we're going to now say E times the drift velocity times B, the magnetic field that you put on it. Okay. We also know that it should be fairly uniform so that the voltage, which is equal to the integral of E dot dl, right? Actually, V equals negative integral E dot dl. Since we know that, we can say, oh, well, this will be straightforward because the electric field is going to be uniform. So this is just going to be EH times the diameter of the wire. Okay. Now, this tells us that the electric field, the electron charge cancels out, and we have EH is equal to V drift velocity times B. So now I can combine this with this and say that EH times D is actually going to be equal to the drift velocity times B times D again. Okay. But that's also equal to just the electric potential. So if you actually measure the voltage difference from one side of the wire to the other, you'll get this E that really is our Hall voltage. Okay. And we can now use that and say, okay, well, evidently the drift velocity is equal to the Hall voltage over the magnetic field used times the diameter of the wire. So remember, we calculated, what was it in chapter 20, I want to say 25, we calculated the drift velocity, and this can be compared to actually that drift velocity. So for instance, let's imagine a wire. Let's imagine a wire in, I don't know. Let's call this example 2, by the way. What time is it? Okay, plenty of time. So example 2. Let's imagine a wire has a 2.00 millimeter diameter. And it's submerged in a magnetic field of 2 Tesla. Okay. And let's say the actual voltage, the Hall voltage, was measured. It's going to be a very small amount, by the way, to be EH equals, let's say 3.0 microvolts. Since that's the case, let's determine the drift velocity. So what is the drift velocity? Of the electrons. So that's our question. Well, we have right here that the drift velocity is supposed to be equal to the voltage of the Hall effect divided by the magnetic field times the diameter. So we can put this in, we'll get 3.00 times 10 to the negative 6 volts over, now the magnetic field is 2.00 Tesla, and the diameter is 2.00 times 10 to the negative 3 meters. So basically I'm going to divide by 4, that gives me 0.75. And then 10 to the negative 6, and this 10 to the third comes up top, so it'd be 0.75 times 10 to the negative third. And that should be meters per second, which you can actually work out by realizing the relationship between the Tesla and meters. For instance, it turns out that magnetic field is equal to, well, yeah, I'll just tell you that it works out right now. When we cover Ampere's law, I have a better explanation of why it does work out. I just don't want to open that can of worms yet. Okay. So this is 0.75 times 10 to the negative third, which is also 7.50 times 10 to the, notice I multiplied this by 10, so I got to divide this by 10, so it'd be minus 4 meters per second. And again, we get a very small drift speed for the charged particles carrying current. And again, that seems kind of mysterious because, you know, the instant you flip on the light switch, they even did this in the movie Arthur, by the way, the instant you switch on the light switch, boom, the light comes on. I mean, I'm sure there's a minor delay, but it's really, 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 really so minor that we can't detect it without doing some precise stuff. So you might say, well, how the heck are these things moving that slow and the current move that fast? Well, the current's not necessarily moving this speed. The current, in fact, we can figure out works out at about the speed of light. And what's going on is it's more like you've filled a water hose up with BBs, or excuse me, with marbles, and the whole water hose has continuous strings of marbles touching each other all the way in. If you just barely touch one of these ends, the marble on this end, say, then that instantaneously, because all these things are touching, instantaneously pops out the one on the far end. So that's sort of more of a better model of how current works, as opposed to seeing little particles just going off into the distance. Okay. Another thing you can do with this understanding of magnetism and the way it acts on particles is you can actually take and allow electric and magnetic fields to help you out and figure out, say, how much mass something has. So for instance, if you're separating uranium isotopes because you want uranium 235 and you have uranium 239 or something like that, and I might have reversed those, I never can remember, I have to look it up every time. But basically, if you're wanting to make a nuclear weapon out of uranium, you have to have a certain isotope, and it has to be a large percentage of that isotope, and all the rest have to be gotten rid of. So one of the things you can do is shoot these nuclei of the uranium into a magnetic field, and they're going to all be traveling. Let's see, this will be example 3. So you say this is a big positive thing, it's traveling this way, and it has a mass m1, and it's going to go into a magnetic field. Let's say QV is this way. I want the thing to go down, so I'm going to say the magnetic field points. I'm going to say the magnetic field. No, I don't want it to point that way. I want the magnetic field. So QV cross B. Okay, I want the magnetic field pointing out of the page. Okay, so the force on this charged particle would be QV cross B. That's the magnitude of, I mean, that's the actual vector itself. Now the QV is this way, the B is coming out this way. So if you used your right hand rule, you would see that would force the thing to go down. Well, we'll know the magnitude then, of course, since they're perpendicular, the magnitude of force is just going to be Q times V times B. Okay, so let's say this thing has a charge Q1. That's the force that's going to act on it. Well, that force is going to tend to make it go in a circle. So it's going to be M like V squared over R. And that, of course, is M1 and R1. And this is Q1 and V1. Okay, so it's going to go into a circle. But if you have a little hole down here, say for one radius of a circle, and then have another hole over here for a different radius of a circle, then this hole will catch one particular mass object, and this one will catch another. Because you can work this out, you can see, wait a second, I can cancel out one of the velocities, V1, with one of these, and ultimately I'll get R1, or let's just say R for the more general case. R is going to be equal to M times V over B, over QB. Right? So R would be equal to that. So when you have it for M1, R1 would be M1 V1 over Q1B, like that. You're always going to use the same magnetic field. But if the thing has a larger mass, then it's going to be a larger radius. So this is where your big masses go. And this is where your small masses go. And you can even, you know, try to separate them out by having several different areas. But by doing that, that's one way you could actually say separate isotopes, because you know that one of them has one mass and the other one has the other mass. Remember, uranium is defined as uranium by having the appropriate number of protons. What makes different isotopes is the different numbers of neutrons it could possibly have. And they don't play with the magnetic field because they have no charge. So because of that, the only difference is really their mass. If you send them in at the same speed, because that's rated based on, say, the temperature or whatever, you could, in principle, send them in at roughly the same speed. And then all of this would dictate what goes into what bin, and you could get isotopes separated that way. So that's another equation that you're free to use for a mass spectrometer. So this is how you could do it. When they actually use a mass spectrometer, for instance, in chemistry, you could actually do it this way. where things, different molecules of different mass go into one slot and other molecules go into another slot. And then you'll get this little printout with spikes for all the different elements in there. Okay, you could actually do it on a nuclear scale as well. So that's one of the ways. We actually use spinning centrifuge type devices filled with basically uranium gas at extremely high temperature. And that's one of the ways we use to separate the isotopes. That was in fact some of the things that we looked at before we ultimately went into Iraq, was we were looking for whether they had centrifuges, because those centrifuges require high spec or very precise specs on the devices. So when you see someone buying aluminum to a high degree of precision and it's in a certain shape, there's a good chance that they might be using that for nuclear weapons. So that was really the problem. The downside was it seems Saddam was evidently trying to make the world think he was doing that just to keep his country safe, maybe. And we sort of went on some intelligent that was meant to confuse people. So anyways, that's kind of a neat little backstory to all that. And, you know, it ties it back into everyday life. So anybody have any questions on that? So you can look at questions like, let me see if I see any more in the back of the book that you might want to try, or the end of the chapter, I should say. Yeah, I'd say like problem number 9 is a neat one you can work on just to make sure you know sort of the ins and outs of it. I was looking for another one integrating an arc of wire. I don't see any good ones there, but we'll do more of that in the next chapter, which is chapter 28. So we've actually finished chapter 27 now. I've given you enough of the examples of the type that you need to see, I think, and you've got plenty in your book as well. So you can still, you know, still need to make sure you learn all those examples. And when I say learn them, I mean, you should be able to cover the book up for a given example where you can just read the question and then solve the problem without looking at the answer. If you can't, then you haven't learned it well enough. So you might need to stop about halfway through because you forgot some step or something like that. Then you need to look back at the solution, read it over again, see if you can get enough information to get started again, and then finish it. Again, if you run into another problem, then you stop and take another look, a quick peek, close it again, and try it again. And then keep doing that until you can do that example from scratch, okay, to the end without looking it up. That's the way you master these things. And it would help if you actually read the words that they're telling you and maybe even put them in your own sentences. So if you actually write sentences saying, I'm doing blah, blah because of blah, blah, right? That's a very good way of making yourself understand problems. Is trying to articulate exactly why you're doing what you're doing. It's not easy, okay? And probably, unless you're super precise and mathematically minded, you probably have words that really construe a sentence that's not actually 100% correct, but it means the right thing to you, so you can work it out. And then over time, you'll learn more so that you can change those wordings to the more appropriate one, okay? And anytime you write something like that, feel free to turn it into me and ask me, you know, whether that is correct. So I'll help you that way as well. Anybody have any questions before we jump into chapter 8?
Done here.
Okay, thank you. I'm glad for anybody that replies. So in chapter 28, what we're doing is, it's actually called sources of magnetic field, and we've learned, hey, magnetic fields exist in basically. A lot of it was found in a place called Magnesia in Asia Minor, and that those things were given the name magnetic. We know that magnetic fields are actually sort of exist. They definitely exist in some sense, but anyways, they exist, and they apply forces to currents, and they also apply forces to moving charges. Now, if a charge is sitting still, they don't apply forces to them at all, but they do apply forces to moving charges. So if you have a positive charge or a negative charge, if it has some velocity, then you'll actually get a force out of it. In fact, that's not unlike how an antenna works. So if you think about a car antenna, which I'm going to show you here, A car antenna back in the old days was just a piece of metal that stuck up. Okay. The nature of a metal is that it's got all these free electrons that are just free to move. They're not tethered to their atom that well. And what happens is this electric field comes by oscillating in one plane like this. So let's say the electric field is polarized vertically. That means its wiggle is vertical. It's actually moving this way. And in fact, it's accompanied by, check this out, it's actually accompanied by a magnetic field that's perpendicular to it. In other words, in this case, it's out of the page and hangs around just like that. So that's really what light is. That's what Maxwell was able to discover. So the neat thing is this electron sitting right here, it's just sitting still. So and then all of a sudden an electric field comes by, which points this way. So I'm thinking of maybe this part right here, say. So when that part actually hits, say, this electron, then the electron started, even though it was at rest, it started to accelerate. So it went from here to here to here. I don't know why I'm making it bigger each time, but I'm trying to make them the same size. I just wanted to make the distance of separation between them a little bit bigger each time. Bad day. Anyways, so let's do this and then this. So I'm looking at, say, every 100th of a second. So we see what's happening is the electron is now moving this way. So it's now gained a velocity this way. Because of that, now the magnetic field can do something. So when the electric electron is actually moving this way, that means QV is this way, but the magnetic field in fact sticks out of the page. So in order for me to do that, I have to turn my hand this way. There's my QV. Remember, Q is negative, so it's the opposite direction of V. So the magnetic field points out of the page. That means it feels the force this way. So it gets a force QVB, which is actually E times V times B. And of course, the V happens to be basically the force divided by the mass. And the force, of course, was E times the electric field strength. So there's the force divided by the mass of the electron. So now we have this velocity causing this. Now, when I get over here, it's going even faster. So now it's going to go even faster, which means it'll make a sort of a big rectangle or a big loop this way and then come back. So it's going to actually feel that force this way. It'll start to go in a loop like this. And that's basically what's going to happen as the electric field as this electromagnetic wave goes by. It's going to cause the electron to go down and start to go to the right. And then it'll go back and start to go to the left. And it'll just do this. Well, that's registered as a particle moving. So it actually makes an AC current coming out. So out pops a current that looks like this. Now it's out of phase because when the current is going positive, that's the same thing as the electron going the opposite way. All right. But that's the actual current coming out. And now you have to do send it through a circuit that separates out this wave motion and puts in the part of it where it's either frequency modulated or amplitude modulated. So there's a circuit that that engineers, electrical engineers and physicists have come up with where you can separate a carrier wave, which is what this is, from its frequency modulation, which is meaning if you had, for instance, a high pitched sound in a particular register, maybe you would make that frequency multiplied by this. So maybe the individual humps would get closer together, and then other parts would get farther apart like that, and the wave would look something like that. That's FM. If you did AM, the AM would be something like this. That's amplitude modulated. So the actual signal is this little stuff on top of here, whereas this is the carrier wave. That's that. So that's really how an antenna works. But that is a source, say, of magnetism, because lo and behold, electricity, or excuse me, light is a form of electricity. Specifically, it's an electric field that oscillates in one plane and a magnetic field that oscillates in a perpendicular plane, such that those two planes, if you cross E into B, you get the V, the velocity. So that's just something we'll learn later, but I'm telling it to you now. So that is a way we can get magnetism. But another way, as Oersted found, when you've got a current carrying wire as opposed to just an antenna, say you have a current carrying wire like this, and the current's going that way. I told you, if you put your thumb along the wire with it pointing in the direction of conventional current, your fingers wrap around it in the direction of the magnetic field. So what that means is your magnetic field looks like this. And in fact, right here, it's coming out of the page. Right here, it's going into the page. And right here, it's going to the right. Well, it turns out that this magnetic field is inversely proportional to the radius, but it's also proportional to the current. So just a regular experiment can do that. Ultimately, we will learn two laws, one of which will be the Ampere's law, and the other one is called, God, I just lost it, Biot-Savart law. So Biot-Savart law and Ampere's law can both give you what this magnetic field is. It turns out the magnetic field B is equal to mu0 I over 2 pi times your distance away, where that is the R. Okay, this mu0 is defined to be the permeability of free space or vacuum. And that really is supposed to be, I've been trying to read a lot on where this number came from and the word permeability, but it's in some sense related to how easy it is to magnetize space. Okay, in some senses like that. And the other one, the epsilon zero we used in Coulomb's law, was the permittivity of free space. And that was how easy it was to, in some sense, electrify. But mu0 is actually 4 pi times 10 to the negative 7th. And the units turn out to be Tesla meters per amp. So that was that constant I was trying to give you earlier. I needed to introduce this before I could show you that that other thing was going to come out in meters per second. But that's what the mu0 is. It's 4 pi times 10 to the negative 7th. So if you take your 8.85 times 10 to the negative 12th, which was Coulomb squared per Newton meter squared, and you multiply that by 4 pi times 10 to the negative 7th Tesla meters per amp, you get hopefully y'all can see this, 8.85 e to the negative 12 times 4 times 3.14159 times 1 e to the negative 7. Now that doesn't seem like a very valuable number, 11.12 times 10 to the negative 8, or negative 18. But let's flip it over. So I'm going to say 1 divided by answer. So I say 1 over mu 0 epsilon 0 is actually going to be 89.92 times 10 to the 15th. Well, that doesn't seem very good. What if I try this? And actually, if I worked out the units, I'd find that the units would be meters squared per second squared. So you say, okay, wait a second. Maybe if I try the square root of mu 0 epsilon 0 and the reciprocal of that. So now I'm going to take the square root of the answer, square root second function answer. And lo and behold, we get 3.00 times 10 to the 8th meters per second, which is c, the speed of light. Okay. So when I was telling you earlier about how Maxwell puts his equations together in some special way and out pops a wave equation, and there's a little slot for the velocity in a wave equation, because a wave equation is like a second order derivative in space equals 1 over the velocity squared times the second order derivative in time. That's the nature of a wave equation. When he looked in the slot for velocity, he got 1 over the square root of mu 0 epsilon 0. This is about magnetization. This is about electricity and charge. They before that didn't necessarily think those two were completely related, and they certainly didn't think they had anything to do with light. But lo and behold, when he computed this, he saw that was the speed of light that we knew of. Then it was obvious that clearly they're related, and he knew what light was. He knew it was exactly that thing I just showed you up here with the electric field oscillating one plane, the magnetic field oscillating in a perpendicular plane, and then a mutually perpendicular direction to both of those was the direction of the velocity. The velocity. So electric field, magnetic field, velocity, there are 3 parts that make up different axes. Any questions on that? All right, so that's a little intro to chapter 28, which is, as I said, sources of magnetic field. I'm going to do it in a little different order. I'm going to start with the law of Biot-Savart, which is actually the more complicated thing to use. And then we'll use Ampere's law, which is a lot simpler, because I find that students like to learn the simple way after they've tried the hard way. Okay, the simple way is Ampere's law is always true, but it only works to do what we're trying to do with it. In other words, to solve for the magnetic field. It only works in certain symmetry situations, just like in Gauss's law. Gauss's law is always Gauss's law. It's always true. But if you wanted to use Gauss's law to solve for the electric field, that only worked in certain high symmetry situations. Same thing with Ampere's law. It's always true, but it only works in certain high symmetry situations if you're trying to use it to solve for the magnetic field. So I will let you guys go, and I will see you at lab. I did open up the lab stuff. Sorry I didn't do that earlier. And I'll also have your practice test, practice midterm up very, very soon. Like I said, I might even be able to do it during your lab. So everybody's free to go. I'll wait for the last person to leave before I split myself.
Thank you, Professor.
Next day, Professor.
Thank y'all.
I was gonna say I'll be late to lab. I have a doctor's appointment, so I'll be coming at like 3 o'clock.
Okay. And that's to lab today? Okay, no problem.
Yeah. Okay.
Thank you.
I had a question.
Yes.
So I was looking in the grade book, and I was wondering, I was like, man, why is my homework grade so low? And I realized that physics primer and the other like intro homework thing I didn't do. I had it for 2 other courses as well, so I think I probably just forgot to do this one and did the other ones. Had 3 total. I was wondering if there's any way I can still do those, because it's just really basic stuff, but it's bringing down my grade like 15 points right now.
Yeah, they're actually not going to, they're going to count as extra credit anyways. So it right now is giving you a false sense of negative grade.
Okay.
But they're going to be taken out. So I sort of leave that and don't drop the lowest grades specifically so students don't get a little too cocky. So just
Gotcha.
Don't worry about it. I might actually let you make up those anyways. I might actually do that for everybody, since those 2 are extra credit and they're so easy. If I do, I'll send out an email though. Okay.
Okay, thank you. Yeah, because when I
don't
saw
worry
that, I was
about
like,
them harming
oh
your
my
grade.
God.
Yeah, they were optional. You didn't have to do them. So I will
Okay.
drop those eventually.
All right, makes you feel a little bit better. I'll see you in lab.
All right, see you.
Thank you.
I had a question about next week's midterm. I spoke to you about this last week, but since it is like a week from today, I wanted to talk to you about it again.
You said you wanted to possibly take it before you left?
Yeah, either Monday or Tuesday, or if possible this week.
Yeah, no problem. What I'll do is I don't want you missing another class period since you're already gonna miss some. I'll make a separate version for you. So it'll be somewhat different from the one the class gets, because obviously, you know, it'd be real easy for you to accidentally tell someone what the problems were on the test, and they might have enough similarity that you give them an advantage. But so I'll just ask you not to do that. But I'll make it available at some time Tuesday just for you.
Okay.
Is Tuesday good, or would you rather Wednesday?
Tuesday would be good because I have to, I have to